So today we're looking at the development of the derivative, the first half of the house of calculus, motivated by the tangent line problem. So if you recall from y'all's reading, like on the first 2-3 days of school, when we all were reading the student letter, I had y'all read about the priority dispute between Newton and Leibniz. Figuring out a workaround for the tangent line problem was Leibniz's perspective. In the 17th century in Germany, he figured out a way to find the slope of a tangent line, whereas the other guy, Newton, right, he was looking for an instantaneous, velocity question. And even though they were motivated by very different things, the answer to both of their questions was exactly the same. It was the establishment of this function we call the derivative. The derivative then is going to be a function that gives us the slope of the tangent line and gives us the instantaneous velocity, or generally the instantaneous rate of change of any quantity. So they use different notations motivated by different things. Most people have heard of Newton, though, and give him credit because he became head of the Royal Society, and he did for everything he could to make Leibniz a footnote in history. But today they pretty much both get credit for discovering calculus. Leibniz, again, was the tangent line problem. So before we look at the tangent line problem, we need to kind of define what a tangent line is. So off to the side here, if you think back to geometry, you had circles, right? And you probably were first introduced to a tangent line in geometry. A tangent line is a line that glances off of a curve at a single point, okay? It's one point. So finding the slope of a tangent line is a very important thing, okay? The other line that we're going to use today, which is also an important thing, but not as earth-shattering, is this one. If you extend a chord on a circle, it intersects it twice. We call this a secant line. Now, why is the tangent line problem a problem? Well, here's the deal. A secant line is not a problem because algebra requires you, when you're finding slope, to have how many points? How many points do you need to find the slope of a line? 2, right? And then it's the change in the y over the change in x, or as we commonly write it, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You need 2 points, x sub 1, y sub 1, x sub 2, y sub 2. We call that the difference quotient. So I'm going to define that right away. We'll be using that all year long. The difference quotient. That's nothing more than the slope formula from Algebra 1. Okay? So if you wanted to find the slope of the secant line and you knew the equation of the circle, you could find 2 points on the circle very, very easily and then compute the slope of the secant line. The slope of the secant line turns out to be the average rate of change. So in Algebra 1, you probably were figuring out average rates of changes. But the tangent line posed a problem because a tangent line glanced off a curve at a single point. And how many points do we need to find the slope of a line? 2. So how do you find the slope when you need 2 points and you only have 1 point? Well, if you choose another point on that line that's not on the circle, now you're just guessing. You lose the accuracy and you lose the point altogether. So I only know 1 point on the circle, so I only know 1 point on the line. That was the problem. How do you find the slope of a line when you need 2 points and you only have 1? Well, if you're Newton or Leibniz, you know what you do? You invent a whole new branch of mathematics that cleverly circumvents this whole needing an extra set of point or a set of ordered pairs. You can get around it. So we're going to explore how they did that more or less by looking at the function 3x minus x squared. I have the graph of it right there. If I asked you, how fast is this graph changing at x equals 1? First of all, let's go up and see where that comes into contact with the graph. Right there. It looks like it's at 2. But I'm going to put a big dot right there. So here's the point 1, f of 1, also known as the point 1, comma 2. All right. If I ask you how fast the graph is changing right there, what would you say? At that dot, at that point, in that instant, how fast is that graph changing? 2. 2 what? How'd you come up with that? 2 over 1? You mean at that moment it's going up 2 units for every 1 it's going to the right? That's a pretty good eye if you could spot that from there. Most people don't even understand the question. How fast is the graph changing at that point? So let me kind of back up a little bit. We could talk about just generically the y values. We're not measuring anything but just height above the x-axis. The y values are going up and the y values are going down. So the first thing you might say is at that point the y values are increasing, right? But then I might ask, how are they increasing? Like at what rate? Well, all you can really say is because the graph is steeper to the left and a little bit flatter to the right, the graph was going up a little bit faster at a faster rate to the left, and it's going to be going at a little bit slower rate to the right. You would only be able to maybe qualitatively tell me how fast it's changing. And we want a quantitative rate of change number, like 2, like what you came up with. Now, from the Newtonian perspective, this question didn't even make sense. How fast is that thing moving at that moment? Well, it's not moving at all, right? It's a fixed point. It's a single point. You actually have to have some time elapsed to see something move, right? So imagine that this thing was moving. This blue dot was moving along this curved path, and you just took a picture of it right there as it passed through the point 1, 2. Now you would want to be able to figure out how fast was it moving in that instant. That's what Newton was trying to figure out. Namely, how fast were the planets moving in their orbits at any given time, because it's not at a constant speed. Leibniz, as it turned out, was trying to answer the same question, but he was trying to figure this out. What is the slope of the tangent line at that point? So we're going to take it from a Leibnizian perspective. It answers the same question, instantaneous rate of change and slope of the tangent line. So the algebra of the day required another point. So here's what I could do. I could choose another point somewhere on the graph. And let's do that one. That one's going to be kind of a bad choice. But there's the point I'm interested in and another point on the graph. I could compute that average rate of change, that slope of that secant line, and I could say that's a pretty good approximation of the tangent line slope that I want. I'll highlight the one that I want. Well, that's going to be a pretty bad approximation, isn't it? What if I choose another point then besides that one way over there? What if I choose it over here? That one's a little bit closer. Well, I can compute the slope of that secant line and say it's a decent approximation for the slope of the tangent line. But once again, that's a pretty horrid approximation because the secant line is a positive slope and those are giving me negatives. So let me choose maybe more judiciously. What if I choose a point right there? Let me choose a different flavor now. The slope of that secant line might look like this. Now we're getting somewhere. Now that second point that I'm choosing is close enough to the one I want that at least I'm getting the same sign. So I could let the purple line slope be an approximation of the tangent line slope. But can we do better than that? Yes. I can pick a point that's even closer. And now it's going to look something like this. Now that secant line slope is going to be even better approximation of the tangent line slope. And if that was even better, what could I do instead of using this x value? Get in closer. So now you can already kind of see the idea of the limit in play, can't you? If I choose that second point closer and closer and closer and closer to x equals 1, my secant line slope, which I'll show you right here, is going to get closer and closer and closer to the slope of the what? Tangent line. And as long as I have two distinct points, I can still compute the difference quotient, the average rate of change, right? The calculations may be tedious, but I can still compute them. So that's what we're doing down here. Let's jump down here and say I'm going to set up the difference quotient between the point 1, f of 1, which is the point I'm really interested in, and then these are going to be my second points. So the first extra point I'm going to use is 1.5. That's a half unit away from 1. The slope of that line should be then f of 1.5 minus f of 1 all over 1.5 minus 1. You all okay with that? Now look at the tedious calculations already. If I don't have a calculator, I would have to plug a 1.5 into this function to get the y value. I'm not going to do that. But back in the day, they would look forward to those kind of calculations. Well, instead of choosing the point to be 1.5, which is a half unit away, let's choose that second point to be 1.1. So now my points are 1, f of 1, and 1.1, f of 1.1. Let's just set up the slope of the secant line. M for slope. Now it's going to be f of 1.1 minus f of 1 all over 1.1 minus 1. Now that should be pretty good because I'm using a second point, bless you, that's only 1/10 of a unit away. But the calculations are still tedious, so I'm not going to do them. But you can see the idea here. Let's then go ahead and set up the difference quotient. Oops. Let's set up the difference quotient for 1f of 1 and a point now that is only 1/100th of a unit away, 1.01. So the slope now of that secant line is f of 1.01 minus f of 1 all over 1.01 minus 1. Now I lose the ability very, very quickly to keep drawing another secant line that is closer and closer and closer without making it actually become the tangent line. There's a finite ability for us to draw it differently. But with calculations, I can keep going indefinitely. Let's go ahead and set up the secant slope between the point 1, f of 1, and a point that is now only 1,000th of a unit away. The slope of that secant line, it would be f of 1.001 minus f of 1 all over 1.001 minus 1. So think about how tedious that calculation would be without a calculator to compute f of 1.001. Our function is 3 times input minus input squared. But I could compute that, and that would be a very, very close number, probably to the slope of the tangent line, which is what I'm really after. Okay, I'm going to show you a different way to compute these, because this is where mathematicians and scientists get smart. Rather than set up this difference quotient and evaluate it over and over and over again, that's going to be arduous, especially without a calculator. We're going to do this. I'm going to get rid of all of those right there, and I'm just going to choose one other point. I'll say it's right here. And I'm going to set up a ratio to find the slope of that line, the slope of the secant line. I'm going to put m subscript SEC for secant line. But I'm going to be a little clever in how I define that other point. I'm not going to pick it to be like 1.5 or 1.01. I'm just going to define it to be, in general, h units away from the point that I'm interested in. Okay? So now I have the point 1, f of 1, and this point is 1 plus h, f of 1 plus h. So see what I'm doing there? I'm defining that second point to be h units away from my first point. So if you want to come down here, in this example A, h was 0.5. It was a half unit away. In part B, h was 0.1. In part C, h was 0.01. In part D, h was 0.001. So again, to emphasize the idea of the limit, you can already see as the 2 points converge towards each other, what's happening to my value of h, the distance between them. It's getting smaller and smaller and smaller. Let's go ahead and set up this. We're on example 2 already. Find the average rate of change now then between the points 1, f of 1, and this other point that is h units away, 1 plus h, f of 1 plus h. All right, so to do that, here we go. I'll do it right here where I can see them. The slope of the secant line, this is still using the algebraic difference quotient. It's the function at 1 plus h minus the function at 1 all over the change in the corresponding x values, 1 plus h minus 1. Okay, so now I can simplify. That's f of 1 plus h minus f of 1. And by definition in the bottom, the 1's are going to cancel and you're going to left with h. This is really delta y over delta x. And we're just defining delta x to be h, because it's a little bit easier to use h instead of delta x. Okay, so now for my function is 3x minus x squared. So let's go ahead and set it up. F of 1 plus h, well, that's going to be 3 times 1 plus h minus 1 plus h squared. F of 1 plus h, all I did is I took the x's here and replaced them both with what? 1 plus h. Minus f of 1, I think we've already computed it, but let's do it again. 3 times 1 minus 1 squared. Okay, so that's all I did. 3 blob minus blob squared. I plugged in a 1 plus h for the first blob and a 1 for the second, all over h. And if we simplify that, we get a slope to be 3 plus 3h minus 1 minus 2h minus h squared. That's square multiply double square and distribute the negative. And that comes out to be minus 2 all over h. Now if you look what happens in the top, your 3 cancels with the minus 1 minus 2. And you're left with the slope being 3h minus 2h, which is h minus h squared all over h. Now what happens if we let h equal 0? If we let h equal 0, do we still have 2 points anymore? No. If we let h equal 0, we're back to the same problem. H cannot be 0, otherwise we have a single point again. From the Newtonian perspective, if you let h equal 0, you're letting 0 time elapse. And you can't talk about how fast something changes if you don't let any time elapse, right? So h can't be 0. But algebraically, we have a workaround for this, right? When you plug in and get 0 over 0, we know that you could factor the h out, and you get 1 minus h all over h. We get down to this formula. This gives you the slope of the secant line now as a function of h. It's equal to 1 minus h. Of course, h can't be 0. So all of your formulas in physics, this is how they come into existence. People kind of do these for very specific cases, and they extract these generalizations from it. So I wrote this in function form. This now is a simple little formula that will give us the slope of the secant line as a function of h between x equals 1 and x equals 1 plus h. So look how easy it's going to be now to compute my difference quotients. Let me copy this and come back up here to example 1. Using this formula now, it's going to be real easy. What is the slope of the secant line? Well, notice we don't have to compute f of 1.5 and then subtract it from f of 1. Because we did all that work already one time. I just need to figure out what is the slope of the secant line when h is equal to 0.5. Well, plug it in here. What's 1 minus 0.5? 0.5. So the slope of that secant line would have been 0.5 if I would have drawn it from 1 to 1.5. Well, what would be the slope of the secant line now between 1 and 1.1? Well, that's when h is 0.1. If I just plug it in, it's 1 minus 0.1, which is what? 0.9. So remember, when we move that point closer, we're saying that the secant slope is a better approximation of the tangent slope. So it's probably closer to 0.9 than it is to 0.5. Well, over here, when I let h equal 0.1, the slope of the secant line is 1 minus 0.1, 0.01, sorry. What's a buck minus a penny? 99 cents. So the slope of that secant line was 0.99. And look how much easier it is to compute it. I never even have to figure out what 1.01 squared is. I did the work already. And then this one here, the slope of the secant line, when that second point is 1,000th of a unit away, well, it just says to do 1 minus that number. So 1 minus 0.0001 is actually 0.999. And now I think we can answer the question from part 1. Based on our mathematical calculations above, can we now predict how fast the graph was changing at 1? Look at the limit process there. Can you see what the secant slopes are approaching? 0.5, 0.9, 0.99, 0.999. If I did it again for a little closer, it'd probably be 0.99999, 0.9999999. Anyone want to take a random guess what the limit of the secant slopes is going to be? 1. Yes, so here's what we could say. The limit as h goes to 0 of your secant slopes, it should approach your tangent slope. And that's what we're after. So for us, we did this. We took the limit as h went to 0 of our 1 minus h function. And of course, we know how to evaluate a limit by plugging in a 0 without ever making the claim that h had to be 0. You get 1 minus 0, which is 1. And so that's the clever workaround. We know then, and you were pretty close, Pierce. You said it was 2. You're only 1 off. Here's what we know. We know at x equals 1, this graph is going up vertically for every 1 it's going to the right. It's going up 1 over 1 to the right at that instant. Now, in the very, very next instant, it's flatter than that, so it's less than 1. And in the very, very previous instant, it's steeper than that, so it's greater than 1. It's at that moment in time, the slope of the tangent line is 1. Or from the Newtonian perspective, if you were measuring the position of an object in feet on the y-axis against time in seconds on the x-axis, you would say the velocity of the object at that moment, at that instant, is 1 foot per second. That's pretty awesome, okay? Now, the bad news about it is it only works for this equation at x equals 1. If I wanted to figure what the slope of this graph is, let's say right here at 3, I know it's going to be a negative number. I would have to go through all of this all over again, wouldn't I, and figure it out. So here's the next step in the evolution. We are going to, instead of using the point 1, f of 1, we're going to use a generic point, x, f of x. And we're going to treat this as a constant. Treat as a constant. Don't tell the math that it's really a variable. We're just going to treat it like we did the 1 and the f of 1. And then we're going to use that other point still, that's h units away. So here's what it's going to look like. We're going to take the 2y, let me show the points. There you go. Let's do it right here. So here are the 2 points. Instead of 1 f of 1, 1 plus h, f of 1 plus h, we're going to replace 1 with x. This is getting more general, okay? So now the slope of the secant line is going to be the change in the y values, f of x plus h, minus f of x, all over what? The change in the corresponding x values? Bless you. Which, not surprisingly, if you clean that up before you actually make it function specific, you get h again. Because remember, this is just delta y over delta x. We're just using h to represent delta x because it's a little bit easier. Well now, remember your function, f was 3x minus x squared. So now I can set it up. The slope of the secant line between any 2 points, or in terms of the math, the constant x comma f of x, and the other point x plus h, f of x plus h, it's going to be 3 times x plus h minus x plus h squared. There's f of x plus h minus f of x itself, which is 3x minus x squared, all over h. We're just using the same function. 3 times input minus input squared. 3 times input minus input squared. Here's 3 times input minus input squared. 3 times input minus input squared. Okay? Well, just like we did before, this is not a bad formula, because now I could just drop in 2 values, x and h, and figure out the slope there. But this is not going to be any better than if I had set up the difference quotient with numbers. So let's go ahead and just expand it out. Let's do the algebra symbolically with letters and see if we can distill some kind of general process at the bottom. We get 3x plus 3h, square multiply double square and distribute. Negative x squared minus 2xh minus h squared minus 3x plus x squared all over h. Good things should happen in the top now. 3x minus 3x, negative x squared, bless you, plus x squared. And everything that's left has an h in it. So once again, we'll factor the h out. This has a very familiar feel to it. It's like the sledgehammer, because it really is. Now, once we factor out the h, remember, h still can't be 0. Technically, if h is 0, we have backed the tangent line problem. We only have a single point. Or in Newton, we can't talk about a rate of change because we haven't let any time expire. But we know algebraically the mathematical workaround. If we divide out the h's, we get this formula 3 minus 2x minus h. And this now can be used to find the slope of the secant line on that graph between any point x comma f of x and x plus h, f of x plus h. Did I mess something up? Did I not factor out? Well, let's see. I have a 3h, which becomes a 3, minus 2xh becomes minus 2x, and minus h squared. There was an h squared there still. So we're still left with an h. So let's just verify one. I don't want to verify all of them. Yeah, this will give me the slope of the secant line on that same graph of that parabola between any point. I just have two inputs now. I have to know the x value, and I have to know how far the other one is away. So let's just verify one of these. Let's verify this one here. Oops. So in this case, x was equal to 1, and h was equal to 1.1 was 0.0 away. So this, in other words, this is a more general formula for finding slope of the secant lines. I should end up with 0.9. But if I come down here and I plug in, oops, I always paste the wrong thing now. There we go. If I compute the slope of the secant line, when x is 1 and h is 0.1, I get 3 minus 2 times 1 minus 0.1. We're going to end up with 3 minus 2 minus 0.1. We end up with 0.9, which is the same thing we got above. But now, if I want to figure out what the slope is between the points x equals 3 and x equals 3.1, that would be very close to finding the slope of the tangent line at this point like I wanted, right? I can actually use this. Let's see. X is equal to 3 and 3.1 is my other point, so h is 0.1. According to this secant formula, yeah, h is how far away that second point is from the one I want. And so if my formula now has two inputs, I can plug in both my inputs. I would get 3 minus 2 times 3 minus 0.1. And that comes out to be negative 3.1. So you could probably infer from there, just with that one calculation, the slope of the secant line between, let me try and draw it, between x equals 3 and 3.1, which would be right there. The slope of that secant line was, what do we say? Negative 3.1. Could you use that to infer what the slope was at 3? Well, maybe not. Here's the magical step. Here's the magical step. If I take this again, this little expression, and I take the limit as h goes to 0. If I let h go to 0, that forces the 2 points to converge on each other of 3 minus 2x minus h. I know that I can evaluate that without saying that h has to be 0, right? We already divided out the 0 over 0. When I plug in, I get 3 minus 2x. This right here becomes not the slope of the secant line. This becomes the formula that gives you the slope of the tangent line. And now notice it only has one unknown. This is the holy grail. If you take the limit as h goes to 0 of your secant line expression, when you define that second point to be h units away, when you let h goes to 0, you're going to get the equation for the tangent line. We call that function not m subtangent. We call it f prime of x. That's how we read it. We read that as f prime of x, and it's known as the derivative function. And this is the holy grail equation that the calculus gives us that Galileo never could find. Galileo rode balls down inclined plane, and he measured the height of the ball at two different time intervals, or 2 different times, and calculated the tiny interval in between. He did all the average rates of changes, but he never could get the instantaneous rate of change. Why is this so important? Well, let's look at it. Let's come back up here to the very top. Now to answer that original question, how fast is that graph changing at x equals 1? You want to know how fast f is changing at 1? Well, if this is f prime of x, I just need to figure out what f prime of 1 is. It's 3 minus 2 times 1, which is 1. It gives you the slope of the tangent line, the instantaneous rate of change. You want to know how fast it's changing right there at 3? No problem. That's f prime of 3. That's 3 minus 2 times 3. That's going to be negative 3. That's awesome. Let's do one more. How fast is the graph changing right here at 2.5? You want to know how fast it's changing at 2.5? That's f prime of 2.5, which is 3 minus 2 times 2.5, which is Negative 2. Yeah. That gives you like the speedometer. It tells you exactly how fast the graph is changing at a single point. Now you can also use it like this. Instead of putting in an x value and figuring out the slope of at that point, what do you know about the tangent line at the vertex here? What type of line is it? It's a horizontal line. What's the slope of a horizontal line? 0. This gives you a powerful way to find where vertices are when they're not parabolas. Instead of plugging in an x and finding the slope, you can actually set your derivative function, as we call it, equal to the slope you want. So that would be 3 minus 2x equals 0. And now you can solve for x, and you get the x location where you have that horizontal tangent line. 3/2 is the same as 1.5. This is called the max-min problem, and this was another motivation for discovering the calculus. It gives you a way to find like absolute maximums right here. If this was a profit curve and you want to know where the maximum profit was, it's going to be at the top where the derivative or the tangent line is 0. And we now have a way to do it. So if we take the process that we did on numbers 1 and 2 and 3, we started with the specific point 1, and then we chose another point 1 plus h, and then we did it for an arbitrary value x and another point x plus h. If you leave it in that form and you stick the limit in front of the difference quotient, you get the formal derivative definition for f prime of x. And here's what it says. If f is some function, then its derivative, which we call f prime of x, that's how we read it, f prime of x, is called the derivative function of f. It's defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Remember, this piece here is nothing more than your difference quotient. It's delta y over delta of x. The magical step is the limit. If you force the 2 points to have a distance between them of nothing, you force the 2 points to converge to each other. And you get the instantaneous rate of change. You get the slope of the tangent line. That's pretty powerful. Yeah, let's kind of go through this. First of all, the notation is f prime. If you start with f, the derivative, as we're going to call it, is f prime of x. If you start with y, you can call it y prime. But there's another notation. dy dx is another notation. And this is where Leibniz gets the last laugh. Leibniz's method was the method of infinitesimals. Newton's was called the method of fluxions. We don't use Newton's notation when we do calculus because he divided by 0, and his notation was kind of cumbersome. But Leibniz never divided by 0, and we still use his notation. So dy dx, as it's called, is the same as y prime. And we use it to denote the derivative of y with respect to x. I like it because it still has the independent variable x and the dependent variable y showing, and it still has that slopey feel to it. It looks a lot like delta y over delta x. And that's for a good reason. It is. The derivative is a slope. And delta y over delta x is your difference quotient. That's the slope of the secant line. The difference between delta y and dy is called the differential of y, is Leibniz said delta y was a finite, measurable change in y. You could see it, you can measure it. But the differential of y was so tiny, you could not see it, nor could you measure it. You could not measure it either. And dx similarly was an infinitely small, non-measurable change in x. Now, when you call something infinitely small, you're calling it an infinitesimal. And so that's why Leibniz called his method of calculus the method of infinitesimals. He never divided by 0. He kind of had the idea of the limit encompassed in his ideas, but he didn't use the limit notation. And Newton certainly didn't use the limit notation. He just divided by 0. Okay, and I'll show you that in 2.3. But we call that dy dx, and it's another name for the derivative. Now, if a function has a slope of a tangent line at a point, we say that its derivative exists there, and we say it's differentiable there. So a function that is differentiable at a point just means that its derivative exists there, which now means the slope of the tangent line exists there. The instantaneous rate of change exists there. There are some places where a function's derivative does not exist, and we'll get to that probably tomorrow. Here's the last thing I want to do. We have to memorize this. I kind of showed you where it came from. I want to do it now for this other function. It says if f of x is equal to the square root of x minus 2, graph it and describe what the y values are doing and how they're doing it. Okay, so x minus 2 is your radical function. It's moved to the right 2 units, and it looks something like this. So what would you say the y values are doing from left to right? Would you say they're increasing or decreasing? Yeah, they're increasing. How? At an increasing rate or decreasing rate? As we go to the right, are the y values going up faster and faster or less and less fast? Less and less fast. So the y values are increasing at a decreasing rate. If you were to think of the tangent lines, like here's my little meter stick, you can have like a tangent line surfer. Think of the tangent line as being the line that would surf the curves. They start off pretty steep and positive, and as you go to the right, the slopes of the tangent lines are getting smaller and smaller. So even though the y values are increasing, it's at a decreasing rate. So the slopes themselves are tapering off. But that's about all you could tell me right there. Qualitatively, the y values are increasing at a decreasing rate. We want to come up with a derivative function that will allow us to just plug in any value of x and not find the y value, because we already have that function right here, but find the slope value at that point. All right, so in the 5 minutes that remains, we're going to do what Galileo could not do. You ready? You ready? He's going to be very jealous. F prime of x is what we call the derivative function, the slope function. We're going to write out the definition first. It's the limit as h goes to 0 of f of x plus h minus f of x. That's the change in the two y values, remember, all over the change in the corresponding x, which we just defined to be h instead of delta x. With the limit in front, it's the slope of the tangent line. It's f prime of x. Now we'll make it specific for our function. We're going to plug in an x plus h first for x, and we get the square root of x plus h minus 2. Minus the function itself is the square root of x minus 2 all over h. Now that's the setup. If you try to evaluate the limit right now by direct substitution, you're going to get 0 over 0. And you know what that means? It means you set it up correctly. Way to go. Because 0 over 0 is undefined. You are using the same point. You're back to the tangent line problem. You haven't let any time elapse. You have no rate of change. But if you look at it now, from our experience, that sure looks a whole heck of a lot like a limit from 1.4 that we're used to evaluating. Don't we know how to do that? How would you evaluate this one? What was the method? RATCON. So the reason we studied all that in isolation in 1.4 is so when you set up your limits and you get them, now you can evaluate them very, very easily. So we're going to multiply by the conjugate, x plus h minus 2 plus the square root of x minus 2 all over itself. These are the algebraic workarounds. The goal is to get rid of the 0 over 0 problem. All right, so now we're left with x plus h minus 2 in the top, minus the quantity x minus 2. All over the bottom is just h times that whole wonderful thing. So I am going to go a little bit more quickly through the algebraic computations because you're not learning them, you're just performing them. In the top, if you distribute the negative x, your x's are going to cancel, your 2's are going to cancel, and you're just left with h. So I'm not even going to show that step. Distribute and combine like terms, you're just going to be left with an h. And now, of course, if we plug in a 0 now, we still get 0 over 0, which is good. That means that we're still doing it correctly. But instead of letting h equal 0, we know that when we evaluate a limit as h goes to 0, we're really not claiming h equals 0. So once that divides out, we use direct substitution, and I'll come over here to a new line. F prime of x, then, when you plug in a 0 for any h that remains, and there is one right there, you get 1 over the square root of x minus 2 plus the square root of x minus 2. That's 1 over 2 square root of x minus 2's. And there you go. If you listen carefully, you can hear Galileo grumble. This is the holy grail plug and play, drop in an x formula, and then figure out what the slope of that graph is at any point. Por ejemplo, part B, find the slope at 6. Well, let's call this 6 right there. I want to find the slope at that point, the instantaneous rate of change. I now have a function I can use. That's just going to be f prime of 6, which according to here, if I plug it in, that's 1 over 2 times the square root of 4, which is 2. I end up with 1/4. That's the slope of that tangent line. It's also its instantaneous rate of change. At that instant, The graph is going up 1 for every 4 it's going to the right. Okay, I'm plugging it in right here. How have we been getting rid of h's? Once we get rid of the 0 over 0 problem, remember any h that remains, we just use direct substitution on. Yeah. All right, let's do one more. Let's do it at 27. 27 is way out here. Notice the tangent line is a lot flatter as you go to the right. Well, I want to know what it is quantitatively. So here we go. It's just f prime of 27, which when you plug in is 1 over 2 times, let's see, 27 minus 2 is 25. The square root of 25 is 5. You get 1/10. You get 1/10. Now here's the cool part. Where is this function f of x continuous? For what values of x is it continuous? Everything except greater than or equal to 2. Good. Okay, this function is continuous for all x greater than or equal to 2. If differentiable means where do the slopes exist, is it differentiable also everywhere to the right of 2? Well, you would think so. Let's see. If I use my little curve surfer here, which is my meter stick, I'm going to hop on out here and start going back to the left towards 2. Now my slopes appear to be increasing. What's happening to the slope right there at 2? What type of tangent line do we have right there at 2? We don't have a vertical asymptote, but we have a vertical tangent line. We say we have a vertical tangent line. And what's the slope of a vertical line? dne. It's infinity. So even though the function exists there, the graph's derivative does not, and that's going to affect its differentiability. We'll pick up there tomorrow. But congratulations. You just kind of made through the evolution of the derivative by way of the limit process. Have a great afternoon.